Hi, this is Charles Maggio. Welcome back to R for Epidemiology. In this screencast, I want to introduce the Kaplan-Meier or product limit approach to modeling disease outcomes. So far, we've spoken about risks versus rates. We've spoken about how risks are binomial. Rates can be modeled exponentially, but rates can also be modeled with another tool that's actually quite more popular. It's called the Kaplan-Meier, M-E-I-E-R, or product limit method to disease modeling. And what exactly is going on here? Well, like I said, if you can assume equal observations over time, you might be able to calculate a risk, which is just simply y over n. But that assumes equal observation over time. If you can't assume that, you may want to consider a rate based on an exponential model, which is the number of outcomes over, let's say, person years of time. But that has a similar assumption. An exponential risk, as I said, I mentioned that it was exponential risk is 1 minus e to the minus lambda times t. Just put that off to the side there. But it assumes, it has its own assumption, it assumes a constant hazard over time. And in fact, this constant hazard is kind of a strong assumption. It's a strong parametric assumption. There is, though, a non-parametric, or actually semi-parametric, approach to survival data or to outcome data that are based on time, which is, in fact, the Kaplan-Meier or product limit. The Kaplan-Meier method does not have this assumption, the assumption of constant hazard on it. It accounts for right censoring, which is basically when people drop out, which is probably the most common or most important type of censoring in these data, which is basically dropouts or lost to follow-up for some reason of some kind. But the one thing that actually distinguishes Kaplan-Meier as opposed to other methods, like the exponential method, is that we are only interested in when an event occurs. Now, what exactly do we mean by that? Well, we're going to talk about that in a minute. Basically, what we're going to do is, for Kaplan-Meier, we are going to basically calculate the survival. The survival function is basically, the survival is from to survive to some time greater than t sub I, and it is the product from over a time period of, this is usually the most, but basically is the number of deaths over the number at risk in a time period where something occurred, and we multiply all those probabilities and add them up and sum them up to get a total survival probability over time. And so what exactly do we mean by this? Well, to be honest, it's easier to illustrate it than to talk about it sometimes, but we're going to talk a little bit about it. What we're going to do is we're going to divide time into intervals. Okay? So divide time into intervals. Then we're going to calculate the probability of survival calculate the probability of survival at each time interval. Then we're going to sum the product of all those probability calculations. And then finally, we'll plot that as a sort of step curve. So, as I said, it's usually easier to just illustrate it than to talk about this sometimes. But here, for example, is, let me just show you this little curve there. I'll make it a little bit bigger so you can see it a little bit better. But here, for example, is what you might see for survival data. And these are data that come from Breslow and Day. So you have 13 patients, and you have the amount of time that they were followed. So patient 1 was followed over a time period of 13. I don't know if it's years or weeks or months or something like that. Nothing happened to him. Patient 2 was followed for 7.2 years, let's say. Nothing happened. Patient 3 was followed for 4.8 years. Nothing happened. Patient 4 was followed for 4.5 times, but had an event of some kind, in this case it was death. And I'm sorry, I forget exactly what these data refer to, but it was death of some kind. So what we see is here, then patient 5 also died after an observation of 7 years. Patient 6 died after an observation of 3 years. But this is the way you'd see survival data laid out, arrayed. What we see here is there's 1, 2, 3, 4, 5, 6, 7 time periods during which something happened and a patient dropped out. These data for a Kaplan-Meier calculation would be arrayed like this, right here. And here then, what we would do is we would say, okay, well, we're really only interested in those 7 time periods where something happened. So in this first time period, someone died. And out of those 13 people, 1 person died. 12 people survived, right? And the probability of survival here was 0.92. As epidemiologists, being a somewhat dismal science, the probability of mortality, though, was 1 minus 9.92. So the probability of mortality in this time period was 0.8. Then we go to the next time period where something happened. Well, then there were 12 people left. At this time period, 1 person died. We calculate that probability as well. And then we multiply that probability by the prior probability, which leaves us with a probability of survival to that time period of 0.85. We subtract that from the total probability of 0.1, and so the probability of mortality in that time period was 0.515. And we just keep on clicking down this way. In fact, there is a neat little example of doing this kind of calculation in R that Tomas Aragon has kindly put into his R book, and I do want to just show it to you very briefly. I'm just going to walk through it. This essentially is a coding your own Kaplan-Meier curve. So let's just walk through this very quickly. First thing we're going to do is we are going to calculate that list of times from that previous, these are the same data from that example. So we calculate the list of times, right? And then we calculate the status for each one, whether someone died or not. Now these data right here that we just calculated are these data right here. So there are list of times, list of statuses. This is just this data right here. If we want to take a look at it, what you could do is you could just say, okay, we can just C-bind it. Why not? Let's say C-bind these 2 vectors we just created, time and status. And here we see it's just that data that from Breslow and Day. That's all these little calculations do. And if you wanted to, we know that time, right, is just this, right? I'm sorry, time is this. It's this vector. So what we're going to do is we're going to sort time first. And this is just the process you go through to creating a Kaplan-Meier curve itself. So if we sort time, what we're doing is we're just taking this time vector, sorting it in increasing increment. Then we're going to basically order or sort the status variable by the time variable, by the sorted time variable we just created, so that the statuses line up to the correct times. You just see that they do right here. We sort of bind them like that. Now, next thing we're going to do is we're going to create a couple of different variables that correspond to this table right here. What we want to do is we want to go from, hold on one second. We want to go from this table right here to this table over here. And so here's the process we go through to do that. We create first a length variable, which is just essentially like the indexing down from the 13th observation to the first observation. And we want to make sure that we want to remove any duplicated times, because we're only interested in the time. So in this particular data set, there was only one time period, 7 and 6 time period, where is it right here? 7 and 6. Oh, here we go. Right here was the exact same time periods. You know, we want to make sure that we don't have duplicated time periods, and we save that into a vector called n sub j. Then we want the number of times that something actually occurred. So we're going to sum these guys over here, so that for each time period we only sum the number of times that there are events. Now, in this very, very simple set of data, this is not very important at all. It kind of looks pretty much the same, but it will make a very different, it makes a lot of difference when you have hundreds of observations. You're basically sorting over the unique time periods. We just did that. Now that what we're going to do is we're going to create these sorted, these unique time periods as well. And then we just do a couple of quick calculations. We calculate the survival at each time period with the number minus the number that survived to that time period minus the number that died in that time period divided by the number that survived to calculate that little survival probability. Then we are going to sum those survival probabilities using the cumulative product function. Then we are going to subtract that from 1 to get the risk or hazard for that particular time period. And now what we do is we just gather all that together into one single data set, to one single object called results. And here basically are the 12 time periods, the 12 unique time periods. And you notice that for some of them, nothing really happened. Now, as I said, we're just interested in those times when something happened. So we want to just keep the times when something happens. And we use this little bit of code here. So it's like basically the d sub j not equal to 0. If we take a look at that now, we see this is essentially this over here. This is, we just basically went through the process of going from this to this using a couple of lines of code in R. And as I said, at the end, you gather them up and we look at what the risk, the overall risk of mortality is. Again, it's a pretty miserable disease. Ends up being like a 76%. Wow, 77% overall risk of mortality. Whatever this particular data set came from, it was a really unfortunate disease. So to calculate, but in any event, what we generally do with Kaplan-Meier curves is we plot them as a curve. So I'm going to do it in ggplot just to show that it can be done in ggplot. And we're going to use the qplot function in ggplot. We're going to plot the number of, basically the probability of death by the time period using a step figure. And this is kind of what a survival curve looks like for these small data. And you can see it's kind of exponential. If you have enough data, it actually starts to the Kaplan-Meier really starts approximating the exponential distribution. But in any event, I think you could see from this very brief example that it's not that hard to actually calculate these Kaplan-Meier curves. What I would recommend is this code is on the slides for this course. Take a little time to actually go through it. I think if you go through the process of actually calculating one of these Kaplan-Meier curves, you learn it to an extent and in a way that you otherwise wouldn't, and it's really worthwhile doing that. And it does illustrate some of the nice aspects of using a program like R to help you understand this stuff. In any event, that's Kaplan-Meier survival curve. In the next talk, we'll really talk a little bit more about proportional hazards and really how to do it using the tools that are available in R. But you don't have to code your own.